How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at the energy of ionic bonding, the Born-Haber cycle. So objectives: interpret and create Born-Haber cycles to represent the energetics involved in ionic bonding, basically talking about all the energy changes for the process, and explain what lattice energy is and its role in ionic bonding. So, quick review: ionic bonding, what is it? Basically, one atom loses an electron and another atom gains that electron, or multiple electrons. So here we have sodium lose an electron, giving it to chlorine. Sodium becomes a positive ion because it got rid of a negative electron, and chlorine becomes the chloride ion, a negative electron, or a negative charge because it gained a negative electron. So now these atoms have opposite charges and they're attracted to each other. And that's the ionic bond. That's it. Moving on. So ionic bonding and energy. An exothermic process. So the whole process overall tends to be exothermic, but let's take a look at the steps. First step, have to remove an electron from an atom. So here we have sodium, and to remove that electron, we always have to put in energy. It's always an endothermic process. So ripping that electron away from sodium is always an endothermic process. It's got a positive change in enthalpy. So that's just something you can look up. What's the first ionization energy of sodium? There it is. It's positive 496 kilojoules per mole. Second step, gaining electrons. This is where electron affinity is going to come into play, and it's usually exothermic. So that chlorine gaining an electron to become the chloride ion is an exothermic process. You can look electron affinity up for chlorine. There it is. It's negative 349 kilojoules per mole. And if this was the whole picture, if this was the whole process of ionic bonding, then ionic bonds would rarely be exothermic. Because if you take a look, we have ionization energy, which tends to be a positive value, and we have electron affinity, which tends to be a negative. And if we look at this specific example, overall, just looking at ionization energy and electron affinity, we end up with a positive value for our delta H. So that's an endothermic process. How are we getting an exothermic process if, overall these two steps were endothermic? Because we're missing something, all right? We haven't seen the big picture. So we've just created two oppositely charged ions. They're very attracted to each other. Opposite charges attract. The bigger the difference in charge, the more attracted they are. So these ions coming together to form a crystal lattice or a solid is a very exothermic process. It's like you got these two magnets separated over distance and they're super attracted to each other. When they come together, they're going to give off a lot of energy. So that's going to be a very exothermic process. That process is what we use to figure out what the lattice energy is. So lattice energy, the definition is the energy required to completely separate a mole of an ionic compound into its gaseous state. So you start with a solid ionic compound. How much energy you got to put in to make it into a gas? Now it's a positive value for separating ions, and it's a negative value for those ions coming together. Because in order to separate them, you got to overcome that attraction. And if they're coming together, they're releasing that energy. All right, so for sodium chloride, the lattice energy is positive 788 kilojoules per mole. Right, so if we wanted to separate the sodium chloride solid into the gaseous ions, we'd have to invest 788 kilojoules per mole. Which means the opposite way, starting with the gaseous ions and then coming together to form a solid, is going to be the same magnitude but opposite sign. It's going to be an exothermic process going the other way. So coming together means you're giving off energy. All right, the Born-Haber cycle is a way to express all of the energy that's going on with all these steps. So it's a thermochemical cycle that shows the energy associated with each step in forming an ionic bond. Things to consider. So we mentioned electron affinities and ionization energies, but those values are for atoms in the gaseous state. So whenever we're talking about like, hey, we want to start with Na and half a Cl and make NaCl, we have to make sure that everything's in the gaseous state if we want to use the electron affinities and the ionization energies. We also have to concern ourselves with the diatomic molecules because the Cl2, we don't want the whole Cl2, we just want half of it. So in order to use half of it, we have to break that chlorine-chlorine bond. So we're going to have to take a look at the bond enthalpies for the diatomic molecules that we're working with. So let's look at an example, NaCl. All right, so overall, the delta H formation is exothermic, and you can look that up. But we know that overall, it's exothermic because we end up at a lower energy than we started with. All right, and if we're talking about the heat of formations, we start with the elements in their elementary states. So sodium is a solid, chlorine is a gas. We only want half of a Cl2, but it's a diatomic molecule, so we have to have it be Cl2. We can't just put plus Cl gas. All right, so we need to get sodium into the gas phase. So that's going to have to require some energy. To turn a solid into a gas, we have to invest some energy. It's an endothermic process, and that's going to be the heat of sublimation. This, in a problem, if you're being asked to solve for anything, they'll typically give this to you, or it'll be on a table somewhere you can look up. So we go from a solid to a gas, and that's the heat of sublimation. Positive change in H. We've invested some heat. Next, we need to split the chlorine molecule into separate atoms, right? We have the Cl2. We actually got to split it in half. So that's going to require some investment of energy. That's going to be the bond enthalpy. And we're only going to use half of the bond enthalpy because we are only using one of the Cl's in the Cl2. The bond enthalpy is to break that bond. So if I'm breaking a Cl bond, now I have two Cl's, but I only want half of it. So we're going to use half the bond enthalpy for Cl2. And we're going to remove an electron from sodium in the gaseous phase now. Well, that's going to be the ionization energy. It's going to be the first ionization energy because we're removing the first electron. That's the first electron we're messing with. And that's going to be another value that is either given to you or you can look up. So now we have the sodium ion and this electron hanging out. So now this electron can be gained by that chlorine atom. And that's going to be where the electron affinity comes into play. And we know that for chlorine, as is true for most electron affinities, it's a negative delta H. So we go down in energy. We have a negative delta H. So now we have these two ions. We got the sodium plus ion and we got the chlorine minus ion, and they're in the gaseous phase. And we know opposites attract. So this is going to be where the lattice energy comes into play. So the Na plus gas and the chloride ion gas phase come together, form a solid, and that is the lattice energy. So there it is. This is the Born-Haber cycle. It's showing you all the steps in ionic bonding. So the lattice energy, it's a major driving force for forming ionic bonds. You can see that it accounts for the majority of the exothermic process, right? A lot of these were endothermic, increasing our energy. And then we have a couple of steps that are exothermic, and the lattice energy is the overwhelmingly more exothermic process. So the bigger the differences in charges, the greater the lattice energy tends to be, meaning that if I had Na plus and Cl minus, that lattice energy is going to be less than like Mg plus 2 and the oxide ion O minus 2, because a bigger difference in charge means more attraction. But this would even be less than the aluminum plus 3 ion and the nitride minus 3 ion. So as we get a bigger difference in charge, the lattice energy increases. Applications. Generally, with this kind of stuff, you may be asked to solve for the lattice energy by creating a Born-Haber cycle for the ionic bond, and the rest of the process will be given in the problem or can be looked up. So all of these values except the lattice energy will be given, and it's just solved for the one thing you don't know. So example, what is the lattice energy for NaCl given the following? Heat of sublimation for Na is 108 kilojoules per mole. Bond enthalpy for chlorine is 244 kilojoules per mole. First ionization energy of sodium is 496 kilojoules per mole. Electron affinity for chlorine is minus 349 kilojoules per mole. And the standard heat of formation of NaCl solid is negative 411 kilojoules per mole. Well, how are we going to do this? Well, a little bit of Hess's law application. We know that this is the overall change. So this is our delta H for the reaction. And these are all of the steps that we can take to get there. So if we're trying to figure out what is the energy associated with step 4, well, we know that all of those steps have to equal this heat of formation. So we know the heat of formation's got to equal the heat of sublimation, the bond enthalpy, the first ionization energy, the electron affinity, and the lattice energy. I put a little negative sign because lattice energy by definition is for separating, and here we're talking about the opposite process, so threw in a little negative sign. So then you just plug and chug. We know that negative 411 has to equal 108 plus half of 244 plus 496 minus 349, and then the negative lattice energy. So they just figure out the lattice energy is 788. Solve for the one unknown. All right, so summarize. Can you interpret and create Born-Haber cycles to represent the energetics involved in ionic bonding? Explain what lattice energy is and its role in ionic bonding. And that's the video. Hope you found that helpful. We'll see you in class. Okay, bye.